Hello. I trust you found your way here. Let's begin. The new unit that we're beginning is called mechanical energy. And in general, there are 7 types of energy, 7 forms of energy: electrical, light, atomic, sound, mechanical, chemical, and heat. We're going to be focusing on one type of energy called mechanical energy, which is energy of motion and position. Most of the time, if mechanical energy is not conserved, it ends up in 2 other forms of heat and sound. There's a general rule in the universe that energy isn't created or destroyed, it only changes forms. So when you think about the sun, where an atomic reaction takes place, which gives off light, which makes its way to the Earth's atmosphere, which then manifests itself in both light and heat as a useful way for things on the Earth to operate. Mechanical energy, by a strict mathematical definition, mechanical energy is the sum of all kinetic energies in a system plus the sum of all potential energies in a system. And I'm using ME for mechanical energy, K for kinetic energy, and U for the general sense of potential energy. Now, why do we want to study this? Well, mechanical energy is oftentimes conserved, or if it's not conserved completely, we can pretend that it is because we fudge. So in events where heat and sound are minimized or are zero, or very near zero, this statement that the sum of the kinetic and potential energies initially has to equal the sum of the mechanical energies final, we can make mathematical statements with this. A good example of where friction doesn't really come into play would be a simple pendulum. We have a mass on the end of a string. We let it go. That will swing quite a while back and forth before friction finally takes its effect and we lose the mechanical energy in the system. So that's a good example of somewhere where mechanical energy is conserved. Also on the air tracks that we have in the lab, those are pretty darn efficient and do a good job of minimizing friction. And so we can do calculations where we let the gravitational potential energy up here equal the kinetic energy down here, and we can make predictions on how fast this will be going when it hits. If we have something big like a roller coaster and we have very small amount of rolling friction between the wheels and the track, we might be able to use mechanical energy to say, hey, what's the speed at the top of this hill right over here? Here are 2 examples where mechanical energy would not be conserved, and we probably wouldn't try to do calculations that way. One example would be a box sliding down an inclined plane where friction is present. Mechanical energy is probably not conserved there. And we've already talked about the bullet embedding itself into a block, lots of heat, lots of sound. Mechanical energy is not conserved, and that's where we have to rely back on good old momentum, which is always conserved. All right, where does kinetic energy come from? Well, it comes from work. And we know that the definition of work is work equals force times distance. I'm going to substitute in a generic S for distance like we did back on the 5-column chart, because it turns out if we do 2 simple substitutions into the work equation, here we have V squared equals V0 squared plus 2AS from column 4, and we solve that for distance, we can substitute that into the work equation. And we just take good old Newton's second law, F equals ma, and sub that in for force. And it takes on an interesting format. So here's the substitution for the ma, here's the substitution for v squared minus v0 squared over 2a. And we pull the 2 that's on the bottom out in front. And notice that the accelerations cancel. We're left with 1/2 m times the quantity of v squared minus v0 squared. Well, I go ahead and distribute that, and I get 1/2 mv squared minus 1/2 mv squared. And this quantity of 1/2 mv squared, whether it's mv squared or mv0 squared, is what we call kinetic energy, 1/2 mv squared. And it doesn't matter whether we're talking about a baseball or we're talking about atoms, kinetic energy is defined by 1/2 the mass times the velocity squared of that object. Now this little derivation that we've done here with the work equation is what is called the work kinetic energy theorem. Notice that we have a kinetic energy here and a kinetic energy here. This is the final kinetic energy, this is the initial. And so a change in kinetic energy is what happens when you apply work to something that is moving, either to speed it up or to slow it down. And that's called the work kinetic energy theorem. Work equals a change in kinetic energy. Next up, let's talk about gravitational potential energy. And once again, we're going to go right back to the work equation. If we want to take a mass m that's on the ground and we want to raise it a certain height, we are giving that object energy. And the energy that we give it is potential energy due to gravity. And we will use the symbol capital U sub g for gravitational potential. Now, what are we really doing? How do we get that block to go from this position up to that position at a height h? Well, what we're really doing, the force that we're exerting is equal but opposite to the weight, and the distance that we're taking it is the height. So, a pretty quick derivation compared to the other one, gravitational potential energy is equal to the mass of the object times the constant of what planet you're on times the height that you take the object. Here we have an example of something that we did first semester where we took an object and we predicted how fast it would be going right before it hit the ground. And we used v squared equals 2as. We solved for v, plugged in the acceleration of gravity and how high off the ground it was, and we could make a prediction of how fast it would be going before it hit. I'd like to show you the same thing can be derived using mechanical energy. In this system, this has an initial mechanical energy that is mgh. It's the gravitational potential energy of the object. And right before it hits, it's going to lose all of its gravitational potential, and the final mechanical energy will be in the form of 1/2 mv squared, the kinetic energy. And if we solve this expression of energy equals energy, look what we get. We get v equals the square root of 2gh. We have just two separate approaches this year. First, by describing motion and pulling equations off of graphs of motion, we were able to derive this equation. And here we are in January, we've come to the same conclusion, but in a completely different way using energy considerations. The last major thing that I need to talk to you about is elastic potential energy. And in order to understand elastic potential energy, we have to understand something called Hooke's law. Hooke's law is a linear relationship that says most springs can either be compressed or stretched, and that the farther you stretch them, the more force will be returned. So if you compress or stretch a spring just a little, you get a little bit of force. And if you stretch it a lot, then you get a big force. And those look like lines. So if we have three different kinds of springs on here, this one has a slope that's lower than this one, and this one has the biggest slope. What does that mean? Well, that means spring number 3, if you compress it just a little bit, we get a really big force returned. Spring 1, on the other hand, we have to really compress it a lot to even get a little amount of force over here. That's a linear relationship called Hooke's law, and K is the slope of this line when we graph F versus X. And K is the spring constant, and it's measured in newtons per meter. And yesterday in class, we looked up a website that sells springs, and on every spring they sell, they tell you what the spring constant is. It's another way of saying how stiff the spring is. Okay, now another interesting thing that we can do is that work is force times distance. And remember in first semester when we took this axis and multiplied by this axis, that allowed us to find the area underneath the graph. And what does force times distance tell us? Force times distance tells us work. And so the work is equal to the area underneath the force and x graph. And that area is the area of a triangle, which is 1/2 the base times the height. Well, 1/2 the base is x, and the height is f. But remember, f is equal to kx. So we can 1/2 x kx, and that simplifies to 1/2 kx squared. That's the amount of work that you have to do on a spring to compress it x amount when the stiffness is K. So work is equal to stored elastic potential energy, which is equal to 1/2 kx squared. Here's everything we've done in summary. Mechanical energy is the sum of the potential and kinetic energies in a system. Sometimes it's conserved. When heat and friction and sound can be ignored, there are some really handy ways that we can use this idea. Kinetic energy is simply 1/2 mv squared. A change in kinetic energy is equal to work. Gravitational potential energy is mgh, and elastic potential energy is 1/2 kx squared, where x is how much you compress or stretch the spring, and k is the spring constant in newtons per meter. Okay, here's where we've been going. We've got an elephant, and that elephant is on a certain height on a hill. And at the bottom of the hill, we have an elephant slowing down device. It's a big spring, and that elephant's going to hit this, and it's going to compress this spring right here, X amount, if we know K, the value of the spring constant. Well, first of all, if we use mechanical energy, we say the elephant only has gravitational potential energy at the beginning of the problem. That would be mgh. At the bottom of the hill, the elephant is going to have a certain amount of speed because all of his or her gravitational potential energy is converted into kinetic. And so we could set mgh equal to 1/2 mv squared. We could solve that for v. Notice that the m's would cancel out. We don't even need to know the mass of the elephant in order to find the velocity of the elephant as he goes by going wee at the bottom of the hill. The other thing that we can do is we can skip how fast it's going at the bottom of the hill, and the amount that this spring is going to be compressed by the time this elephant falls and loses all of that potential energy, that will be in the form of kinetic, which will compress this spring X amount. So we can say, okay, mgh, that's the initial gravitational potential of the elephant, is going to equal 1/2 kx squared, where x is how much the spring gets compressed when the elephant runs into it. So I just wanted to show you how useful this is, and this is all predicated on the fact that we have found frictionless elephant roller skates. Because remember, if friction is a big factor, we can't make these statements so boldly like this. Well, this is a very cram-full video. I hope you've taken the time to pause the video when you needed to so that you could take the notes. But you are not behind the Green Days, even though I was not there today. So you guys have a great weekend, and I will see you next Tuesday. Bye.